Welcome to this explainer. Today, we are absolutely mastering Traversal in singly linked lists in C. By the end of our time together, you will know exactly how linked list Traversal really works under the hood, why we absolutely need temporary pointers, and how to dodge some incredibly dangerous mistakes. Our main goal today? Building a bulletproof mental model so you can finally wave goodbye to those frustrating 3 a.m. segmentation faults. Okay, let's dive into this. Here is our path. 1. The sequential treasure hunt. 2. The core traversal engine. 3. Analytics and edge cases. 4. Architecture and cleanup. And 5. Avoiding fatal mistakes. The sequential treasure hunt. To write flawless C code, we first need to visualize the underlying physical mechanics of how memory actually operates. Traversal simply means visiting every node in a linked list, one by one, from start to end, sequentially. I really want to stress that word, sequentially. It is the foundational, totally unbreakable rule of this data structure. Think of Traversal literally like a sequential treasure hunt. You start with a map that leads you to the very first clue, which is sealed in an envelope. Well, you cannot just skip to the final treasure. You have to open that first envelope to find the pointer to the second, and open the second to find the pointer to the third. You have got to follow the pointer chain without skipping any steps. Now, you might be used to arrays, right? With arrays, you get instant access via an index. Because the memory is laid out completely consecutively, you just do the math and grab your data. But linked lists have no indexes. Their nodes are scattered completely randomly throughout your system's memory. The absolute only way they're connected is through those explicit pointers. And this brilliantly illustrates why there are no shortcuts here. If you want the third element in a linked list, you absolutely must start at the head, jump to node 1, jump to node 2, and finally jump to node 3. Attempting to jump directly there simply does not work. The core traversal engine. So let's build the engine that powers through this memory. It runs on 5 non-negotiable steps. Step 1. Start at the head. Step 2. Create a temporary pointer. Step 3. Check if that pointer is null. Step 4. Process your current node. And step 5. Move the pointer to the next node. This engine will continuously loop over and over until it hits the very end of the list. Let's actually trace this loop step by step through real memory. Notice our temporary pointer. Let's call it current. It starts identically at the head, pointing to 10. We check if it is null. Nope, it is not. So we print 10 and then we say, current equals current arrow next. This moves our temporary pointer to 20, then to 30. Finally, it reaches null. The condition becomes false and the loop stops immediately. And all the while, that original head pointer remains perfectly intact. Okay, I need to pause here for a second because this is the single most vital safety tether in all of C programming traversal. The golden rule. Never, ever modify the head pointer. Well, unless of course you enjoy debugging segmentation faults at 3 a.m. Look at the incredibly high stakes we are dealing with. If you use a while loop and keep doing head equals head arrow next, you permanently lose your reference to the first node. The rest of your list is instantly destroyed, forever turned into unreachable digital dust. The correct way is keeping the head firmly anchored in place and using a temporary pointer to safely explore the list. Analytics and edge cases. The real beauty of our engine is that the boilerplate while loop remains exactly the same. We are simply swapping out the interior logic, the processing payload, based on our objective. Need a count? Just add count plus plus. Inside the loop, need a sum? Toss in sum plus equals current arrow data. It's that modular. Now, what is really interesting here is how we can power multiple complex analytics simultaneously. By layering a count, a sum, and a maximum check inside the exact same while loop, we extract all this rich data in a single big O of npass. It's incredibly efficient. Let's put this thing under pressure and stress test it. How does it handle an empty list where the head is already null? It gracefully bypasses execution entirely. A single node list, it runs exactly once and safely stops. What about a massive list with a million nodes? It scales linearly. Time complexity is strictly O of n because it visits every single node, proving our engine can handle any extreme road bumps you throw at it. Architecture and cleanup. Let's step back and see how this builds into a larger software architecture. We define our node structure in a header file, use utility functions like createNode that immediately check for null after allocating memory with malloc, and build search algorithms that gracefully return a position or -1 if the target simply is not found. But here is the absolutely critical cleanup phase. You cannot just free the current pointer and then ask it for the next node. That memory is already destroyed. Freeing memory correctly requires using yet another temporary pointer inside the loop. We save the current node as temp, advance current to the next node, and only then do we free temp. It is a very elegant leapfrog maneuver, avoiding fatal mistakes. Alright, let's talk disaster prevention. Here are the 4 fatal mistakes. Forgetting the null check, modifying the head pointer, using the wrong pointer condition in your loop, and failing to handle an empty list before trying to read from it. Any one of these will guarantee a segmentation fault or an infinite loop. So the crucial point is really mapped out right here in this diagnostic matrix. Forgetting your null check on an empty list causes a segmentation fault. Modifying head leaves the entire list permanently orphaned in memory. Screwing up the loop condition breaks your logic and causes data corruption. And printing data from a list without checking if it is empty instantly crashes the program. To tie this whole thing together, remember your 4 core rules. Always use a temporary pointer. Never modify head. Always check for null. Always advance to next. This guarantees your traversal will always run in a highly efficient O of n time complexity and a brilliant O of 1 space complexity, because you only ever need a single extra pointer regardless of how massive the list gets. I want to leave you with a concrete practice challenge to test out your new mental model. Right now, load up your C environment. Can you write a function to traverse the list, sum only the even numbers, and safely return 0 if the list is empty? So, what do you think? Can you build the engine?